On your homework, so don't get confused here. On your homework, I have you do this. Of course, it's 0 joules per Pascal. Okay, now I'm not going to be too easy. I'm going to do this instead. Now remember that we actually covered this a long time ago. Equal partition theorem says that the change in U at constant t is 0. Now you're going to prove it. But now the damnedest thing is that it depends whether it's a perfect gas or not. Okay, so instead, I'm going to do du dv at constant t. Now, the adjustments you make for your homework are not hard, but they're not trivial either. So that's why I like doing this. So that you have some idea what the heck is going on, but you still have some kind of challenge to do because I don't want to make this like idiotic. Okay. Now, in these cases, now normally I'd always tell you how to start, but this is brainless, right? You start with the change in U. Okay, so this is the question. You'll start with the change in U because, I mean, there it is. TdS minus PdV. Okay, so again, now as I mentioned to you, this is kind of a funny one. Normally when you're doing derivatives of energy with respect to its conjugate variables, those are the easier derivations. And if I choose a non-natural variable, like on your homework, it tends to be a little harder. This case kind of breaks even, and you'll see why in a second. Okay, now I have to hold the t constant. Now you don't get to decide if that's 0 yet. That's the whole point. You're going to prove that this is 0. Okay, what do? Now again, so I don't leave you hanging, I tell you that you need a Maxwell relation. Okay, dv, it doesn't matter what's held constant, it's always just 1, so that's minus p. Okay, now remember that we're still trying to prove this is 0. Now, as I said before, when you have change in entropy, whenever you have entropy in the mix, you've got a problem that always way complicates things. Now, I tell you, and I'll always tell you this, Maxwell, you need a Maxwell relation. It says that. Question like on this on the test, it'll tell you, use a Maxwell relation. Now that's all I'm going to say, but now here's why I want to do this in class. Here is a big hint. Now you see which Maxwell relation you need. It's ds dv at constant t. Now you look in the cheat sheet and you find it, and there you go, you're done. But now, just so you build some self-confidence and so you know what you're doing, there's a big hint. Let's say I didn't tell you that. There's a hint to figuring it out. All Maxwell relations are built on energy functions. Which one is the right one, A, H, G, or A? Which is the right one for this one? The hint is it's the one at constant V and T, which is A. Right, okay. Now again, this is given to you. A is the one that's all negatives. I almost got it wrong. Okay, so ds, dt, constant T, dp, and I'm doing that thing, I'm doing that in my head. Okay, so now I've got T, dp, dt, and it's, be careful of pluses and minus. That makes it, I mean, if you get a minus sign wrong, you're going to completely blow it. But you can see where we're going here. Okay, T, change in nRT over V with respect to T. It really doesn't matter if volume is held constant. Now you can see where this is going to go. T nR over V minus P. Now what? Sorry, that's not a good T. Okay, now what? Now what do you think? What do you think?
P
minus
T.
P.
Yeah, P minus P. There you go. Now, as you can imagine, on your homework, just change the P's, change the V's to P's. You're going to need a different Maxwell relation. Looks like you'll need Gibbs one. Instead of a dv dv, you're going to have a dv dp. That's why it's slightly harder. And guess what? You'll get 0. So anyway. So very similar steps. Take a step, find a Maxwell relation, and then use P equals nRT. It really isn't hard. So now let me make it hard. Now I'm going to throw a monkey wrench into the whole thing. I only have done this on one question on your homework. Maybe the next homework I'll add. We have one more homework, and I'm definitely tempted to do this on the test. What if P is nRT over V minus NV minus AN squared over V squared? Uh-oh. Uh-oh. What if I asked you to do this for the van der Waals? Let's just keep this up here. Where do things go off the rails? Warmer, colder? Warmer? Ah, right here. Okay, so I'm going to wipe this out. I'm going to wipe this out and begin again because there really wasn't much to that. I try not to do that too much, but I'm going to have to. Okay, T, dP dt. Actually, that's not so bad. nR V minus NV. And there's no T in the next term, so again, you're going to be able to do your derivatives. Not that the identities are on the cheat sheet. Okay, so what do you think, right? You see how it's almost P minus P? All right, you see that? But I've got, instead of nRT over V, I got nRT over N minus NV. It just messes it up, right? Okay, I just tricked you. I just tricked you hideously. That's not the right answer. It kind of is. I'd actually imply give you full credit. But there's actually something else to this. What did you fail to do? Insert warmer, colder.
P for the
Here, right. There's two P's, not one. Minus nRT V minus NV plus AN squared over V squared. You see, what would happen is, you were about to say that the B term messes this up. It's not. It's the A term. See? Those are actually the same. AN squared over V squared. Aha! See, you get a completely different conclusion. Careful about that. Maybe I just take 1 point off, because that's kind of insidious, by the way. I realize that. But there you go. Gas's internal energy does change slightly with temperature because of self-attraction. Now, one way to reconcile that with the equipartition theorem, remember that when I lied to you at the very beginning. I even warned you that a little earlier on. That I said, oh, do the equipartition theorem, the change in U is always zero isothermal. Now, the reason that I said that is because we were just covering this stuff, and I didn't want to start throwing in insane nuances until you've gotten some of this beaten into your head. But the reason that you might be able to reconcile that is that, remember, as you increase temperature, you might start to open up new degrees of freedom like vibration, right? So anyway, that's why you might see an increase in internal energy with temperature. So that it kind of reconciles the two cases. And I mentioned how at room temperature, right, we're really close to thermally populating vibrations, but for the most part they don't count. So there is a slight dependence of U on temperature. U does slightly change at constant temperature. That's why, because of how things are attracted to each other. Okay, I've got one more on the homework. You've got a dH/dV at constant T. Want to see that one? Okay, let's do that one. And then I've got one more example, and that does leave some time for questions, or I've got some more examples if you feel like. Now, maybe I already mentioned this. I've actually just already forgot. I'm getting too old. I do have some on the handout section, the resource section, whatever I called it. The one with the textbook. There's a bunch of handouts there, and those are handouts from previous classes, so I never really harped on them. But there's one towards the end that says example thermodynamic derivations. There's some example thermodynamic derivations. Those are fairly hard ones. So anyway, they're just there. I'm not saying I'm going to ask something that hard, but just so you know that you have those. And I can do more if you feel like. If you feel like you're still a little bit stuck. Again, because you absolutely cannot memorize these. Do not come into the test having memorized these. You have no idea what I'm going to ask. I don't know what I'm going to ask. But I probably will not ask ones I've done in class. And if I do, it's accidental. Okay, so the homework, you do DHDP. So I don't confuse you, let me do DHDP. 0, sorry, joules per Pascal. I stickler on units. How was that? Okay. Now, given that I asked for DH, it's brainless that you start with DH. TDS, and of course these are spelled out for you. I don't want you having them, so I have these memorized, but I've been doing this 15 years, but don't worry about that. I will spell these out for you if you need them. I don't want you getting this, P's and V's switch and getting everything wrong as a result, so I won't do that. So anyway, so this is kind of easy. So then you divide by dP. Remember, you divide partial by partial, and you can hold anything you want constant. So again, now you see why a natural variable derivation is friendly, because I've got a dP. And it looks like I've got myself a Maxwell relation. There we go. Again, with the derivatives with natural variables, you always, one of the terms ends up being easier, so that's slightly nicer. Okay, now this is the kind of question where the question will say you're going to need a Maxwell relation, and that's here because I've got entropy, and entropy is a bear, and I certainly would rather be doing PV equals nRT, but there's no PV equals nRT for entropy. Entropy's formula is KLNW, not CV times T or anything, which would be much better, but anyway. So we need a Maxwell relation. Look in the cheat sheet, find it. But again, if you know this, if you really know this, which is going to be good because it'll just make this go better, and go better means better grades, you should know that you can figure it out based on a Maxwell relation. The one you're looking for is always based on it's just happenstance, but it's always down here. You're looking for one that has P and T in it. What is the energy function with P and T as natural variables? G. It's G, okay. Now again, I can't emphasize enough, this is on the cheat sheet. Do not come in here, do not waste your time memorizing Maxwell relations. If I ask a Maxwell relation, it's going to be cats and barking dogs or something, which is not a joke. Anyway, okay, minus ds, dp, dt. Maybe I'll have mice in it. And I'm doing the sp constant t, dv dt constant p. So there's a little mnemonic to it, and I'm going to put the minus sign over there. Okay, so what have I got? T times minus dv dt constant p. Now, again, when you have dv, when you got the xyz thing, and it's all perfect gas law stuff, then that's you should know you're in a very simple area. This is a gas law. Okay, change in nRT over P with respect to T. You see, these really are not hard at all. Okay. Now, some of you did struggle with this, by the way, and that bothered me. So hopefully I've done, it's another reason I like doing these examples. You should not have trouble with this at this point. Minus T nR over P plus V. Guess what? V minus V plus V. There you go. Yep.
That's T, right? DH, the P at constant T of the all the way at the top. To the left.
Yes. Oh God, yes. Sorry. Thank you. I'll fix that digitally. Cat or something anyway. Yeah, I'll fix that. Thanks for pointing that out. I've actually not made too many terrible mistakes in this class. Normally I'm having to do a lot of video editing. Maybe I'm getting better at this. Anyway, meters cubed. Oh, look at this. A joule divided by a Pascal is a meter cubed. Makes sense. Now, and your homework, again, you do this with volume And you see that it just gets slightly harder right here, but whatever. Right? It's just PV and LFD stuff. So I actually chose a slightly easier one. Okay, now I've got one more that's based on a homework. You have, and I'll write this one out. And I don't know that there's much meaning to this. You know, one of you is asking, what does it mean? And sometimes, sometimes, oh, it's like when a jet flies at 30K. Sometimes I don't know. But I know I can do it. And that's what people like to do. Can I do this or not? Okay, on the homework you do this. Okay, so you do this. Okay, now let me try, because I kind of got challenged on that. Can I make this relevant? Oh, that's hard. This was actually kind of hard. Okay, so I got to change an A, so I have to start telling you about A. A is relevant at constant temperature and constant volume. Okay, now in the oil industry, now constant temperature is a no-brainer. We always try to keep temperature constant, right? I mean, everything you've ever done has a temperature bad. Okay, so that's brainless. Constant volume, I've said it a zillion times, try to avoid that. It's dangerous because if a reaction produces gas, the pressure is going to rise and it's going to explode. But in the oil industry, they do things in constant volume reactors. Careful. Okay. And actually, if you lived when I lived in California, the refineries, those guys had explosions all the time, and they actually would try to hide it. And then they get in a lot of trouble because people would smell the gas. And seriously, they did it all the time, at least once a year. And occasionally people got killed. Okay, so I want to drive A down, and I want to see if I want to change the size of my reactor. Okay, now here's how I can make this relevant. I said that we want A to be negative to drive, spontaneous means A is negative at constant V and constant T. So why am I asking about the change in V? Well, the answer would be, I might want to tell my supervisor whether we want a bigger or smaller reactor, right? And this would answer that. If this whole thing is negative, then A goes down with increasing volume by a bigger reactor. Right, see what I mean? You want negative A at constant volume, constant temperature. That drives the reaction. That means the reaction is spontaneous. More negative A means more spontaneous. That's good. And I'm going to figure out whether, if this whole thing is negative, that means if V is bigger, A is smaller. Remember, smaller A is good. Now, there's a funniness to this, which is at constant entropy. So that means that you have an adiabatic reversible reactor, which, based on my other lecture, literally does nothing. Okay, anyway, now here's another thing I had you do on your homework. It turns out that when you look at the entropy of any chemical that exists at room temperature, it's always higher than its heat capacity. It kind of has to be, and we'll explain a little bit more of that later. Okay, so if S is always greater than CV, it always is. There's no chemical that exists for which that is not true. This is always positive, P is positive, so that means if V goes up, A goes up. That actually would be bad. That'd be bad for a chemical reaction. Anyway, now we know. So you're going to solve this on your homework. What do I have you do? What am I going to do? I'm going to do GG, BP, a constant S. How do I do that? Now you notice that I chose the other free energy, G, and I did its natural variable. So that's why I'm picking this one, because it's very similar, but not the same. Okay, so how do I do that? All right, well, obviously I said DG, so I'm not going to tell you to start with DG, but ask DG, all right? Because that's too easy. Minus SDT plus DDP. I got to remember to give myself more room. I don't know why I do this. Minus S. Sorry, I know that I need to give myself room for this. So remember, divide everything by dP. Constant S. Okay, so again, I knew that it would be kind of the easier sort because I'm taking a derivative with a natural variable. So this guy ends up being easy. Minus S, dt, dP, and constant S, plus V. Okay, now be careful about, okay, this is an exam, when you've written this, you're not done. Now, the reason I would say that is, and of course I want to know whether it actually goes up and down, just like I described here. You're not done here. And the reason is that I don't really know that dT at constant s goes up or down. I don't know that. Now, of course, then you could argue, but you do know that, you just have to do a little derivation. My point is, yes, why didn't you? Hey, so you have to know dP at constant s. We actually did it. We actually did it 2 lectures ago, but I think I'll do it again. I probably would give this to you at the exam. Or I would set you up to do this on another problem. Something, all right? I'm not going to leave you hanging. Okay, now, I want to rewrite this. I know I did it before, but I'm looking for something that has P and S as natural variables. Enthalpy, that's right. And since I'm doing an adiabatic reversible, I don't really expect you to remember this, all right, folks? This is way too hard. This is some of the hardest stuff I've ever figured out with this. But again, if you can just flow with this, if you let me set you up, which I will, and then just get creative and just start doing it. TDS. Oh yeah, H is the one that's all positive. And I like remembering that because oh no, I'm gonna forget this. I forget this. Because I can, it doesn't matter. Okay, right, I see why this is friendly now, because I've got constant S. Changing S to constant S. Oh yeah, so this isn't bad. Oh, this is actually easy. Okay, this is CP. dt, oh yeah, what I'm trying to solve. dt dP at constant S. Oh, this term that's gone. And that's V. Therefore, dt dP constant S is V over Cp. There we go. Okay, so minus S, V over Cp. And that's the answer. And let's factor it just for the hell of it. Minus V, S over Cp. Minus 1. Okay, and again, S is always greater than CP, so that's always positive. Now, I have to tell you that. I'll show you a bit about how I know that. That's coming up. I'm just telling you right now. S is always greater than CP. This is always positive, volume is always positive, this is always negative. So G always goes down with pressure. So there's the answer to the question.
Why can't we use Maxwell's relation at dt over dP constant S?
Here?
Yes.
I don't know. Tell you what, I have no idea. Let me figure it out. Yeah, let's figure it out. Okay, what I need is, oh, that one's based on H2. dt dP at constant S. Yeah, there you go. dV ds at constant P. What did that do? Sorry, it didn't help. Can't do anything. Yeah, yeah, I think I probably have tried to do this to get to the question, to answer this question, but that's non-productive. Now, as I promised, though, it can be. It's just, you know what I would do with this? You know what I would do with this? I would do an Euler relationship. I would do like an Euler relationship, and I would try to figure this out some other method. And I would. I know I would be able to get to, I would get to V over Cp if I just started doing something with this. I would get to this. It just looks like it's going to be like 5 or 6 steps. I'm thinking I'd do an Euler chain. And I don't even know where that leads me. It will lead me to the right answer. It's just I don't know how many steps. This wasn't too bad. So anyway, I've got about 10 minutes left. This definitely carries you through the harder homework. There's calculator questions. There's the chess piece questions. Then there's these. I've actually basically covered all of the homeworks. If you have something for me, I'm here. Huh? Nothing? Nothing? Are you sure?
So you didn't solve for the helmholtz energy.
Question? What was that?
You didn't do the helmholtz.
Okay, so now here's another question. I tell you what, folks, let me do this, and then you can go, and I'll stick around a little bit longer in case you just want to ask me without all the people in the room, which is fine. Right, now, based on what I just said before, I might ask you to do this. Right? That's what you're thinking? Exactly. Yeah, you ought to be afraid of that. So this is part A, and this is part B. Now tell me how, now integrate it to give me a finite. What's the finite change in A? Right? Okay, now here's where this gets really, really odd. Okay, so I've integrated this. It's A final minus A initial. Okay, now I got to start being careful. For one, P hides V in it. I got to be real careful of that. nRT over V. S over CV. Okay, now, you know what? It looks like I got dV over V, and it looks like I got nRT, S over CV minus 1, ln VF over VI. It doesn't look too bad, but there's a huge problem. Entropy is a function of volume, too. Do you know what that function is? It's KLNW. KLN number of microstates. Now you just have to figure out how the number of microstates changes with volume. Right, there's no way to do it. The answer is, look, go to grad school and I will show you how to do this. But for now, no. There's actually some of the changes in A, changes in G, and we're going to talk about this next time. For a gas expansion. So I haven't actually finished, I haven't quite finished everything you need to know. Let me just tell you, for questions 1 and 2, the first 2 questions, change in E, change in G, change in A for magic cylinder questions. We do them at constant temperature. These end up being reversible work, or plus. No, minus. Sorry, they end up being minus reversible work. I'll show you that next time. So I should have got that today. All right, that's isothermal. But if we do magic cylinders that are adiabatic, there's no way to answer them. Not without like a computer or something to model entropy changing with volume. We actually can't do them. So whenever you see me ask G and A on a magic cylinder, it always is isothermal. Because adiabatic changes in A and G are not doable based on what we cover in this class, because you end up always trying to integrate entropy. Entropy is a function of volume and temperature. And it's unfortunately kind of complicated how to relate the two. So I just don't do that. So anyway, I'm glad you asked that. I was actually going to cover that. Tell you what, we still have 5 minutes left, but it looks like you guys are very much need to go. So why don't you go?